Welcome to the Swift Calcs lesson on using the ideal mixture library to calculate with thermodynamic data. Swift Calcs is a built-in library of thermodynamic data on thousands of chemical species based on the NASA Glenn polynomials. To add a new mixture to a worksheet, we can click and drag the Ideal Mixtures icon from the toolbox onto the worksheet, or alternatively, we can use the keyboard shortcut Mixture followed by the space key while in math mode. When we add a mixture item, a pop-up will immediately appear asking us to choose our first species in this mixture. Chemicals are organized by the atoms that make them up, and we can use the search bar to search directly for an item as well. For this example, let's create a mixture to approximate air. I'll start by adding the major component, nitrogen. When I select a species, it'll show me the available range of temperatures for which thermodynamic data is available. Simply click the Select Material button to add the species to the mixture. After adding, I'm immediately asked for the amount of the material that's available in my mixture. Since air is 78% nitrogen, I'll set this to 0.78 moles. Note that you have to provide the amount of the item in either units of mass or moles. If you do not provide a unit, Swift Calcs will remind you to add one. Once I have set this value, my cursor will jump to the variable name for the mixture. I'll call this air, but then I will still need to add my other mixture components. To add more, I click the Add Another Substance link and the pop-up will again appear. I'll now find oxygen and add it to my mixture. I'll set this to 0.21 moles. On the next line, I'll type air to show what is currently stored in the air object. We can see it as a mixture of 0.99 moles made of oxygen and nitrogen. I'll go ahead and add my last component, argon. After adding this component, we can see that the air object is automatically updated and accounts for the mixture change. It is now 1 mole of nitrogen, oxygen, and argon at molar ratios equivalent to air. By default, my mixture is set to standard conditions, 298 Kelvin and 1 atmosphere. I can now ask for various thermodynamic properties of my mixture. Properties are accessed by typing the name of your mixture followed by the colon key. You then type the name of the property that you are seeking. For example, if I'm looking for enthalpy, I can begin typing enthalpy and see the number of options available to me. Enthalpy on its own will provide me the enthalpy of this mixture in mass-specific form. Enthalpy mole will provide it in molar-specific form. Capital E enthalpy will provide the total enthalpy in the mixture. Let's select enthalpy mole. The molar-specific enthalpy of my air mixture at 298 Kelvin and 1 atmosphere is returned. Other available options include entropy, internal energy, Gibbs free energy, density, heat capacity, specific volume, log K, various formation enthalpies and energies, and of course temperature and pressure. For all properties, shorthand versions are available as well. For example, air H will return enthalpy, S will return entropy, U will return internal energy, P is pressure, and T is temperature. We can also set any property to find the thermodynamic parameters at different states. For example, let's set the temperature of our air to 500 Kelvin, and let's set the pressure to 2 atmospheres. We can now ask for the molar-specific enthalpy as before. Here, I'll use the H-mole shorthand. We can see that the value has changed because air is now at 500 Kelvin in 2 atmospheres, whereas before it was at 298 Kelvin in 1 atmosphere. The difference in these values represents the amount of energy required to heat 1 mole of air from 300 Kelvin to 500 Kelvin while increasing its pressure from 1 atmosphere to 2 atmospheres. We can also set other thermodynamic properties. For example, what if we added 100 kilojoules per kilogram to the air? Air enthalpy now equals the current air enthalpy plus 100 kilojoules per kilogram. What's the new air temperature? By adding 100 kilojoules per kilogram to our air mixture, we've raised the temperature from 500 Kelvin to 596.3 Kelvin. We can similarly set entropy, Gibbs energy, or any other thermodynamic parameter and find the new conditions. When setting parameters, you do not need to set H versus H mole. Swift Calcs will determine the correct value based on the units provided. There are also commands to set two parameters at once, such as HP. Air HP equal to a vector, where the first vector is the enthalpy. Let's set it to 6,000 joules per mole. And the second value is the pressure. We'll set to 5 atmospheres. We can see that air is now at 502.4 Kelvin and 5 atmospheres. Other commands that allow you to set two values at the same time include SV, which sets entropy and specific volume, or TP, which sets temperature and pressure at the same time. The full list of available properties and the available commands to set all properties are available in an example worksheet on Swift Calcs called Thermodynamic Properties, which is available in the Help menu under the example worksheets and is also linked in this tutorial. This completes section 3 of the Swift Calcs tutorial. Join us in the next section, where we will discuss sharing and collaboration in Swift Calcs.